Okay, so today we're going to look at section 4.6, applications as models of exponential growth and decay. So this is the answer to the age-old question, when will this happen in the real world? When will I use this? So exponential functions can be used to model many real-world applications. The population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. The function P of t equals 1.25 times 1.012 to the t power models the growth where t is the number of years since 2013 to the nearest thousandths. What will be the population of India in the year 2031? Well, we need to figure out what t is. So 2031 minus 2013 gives me 18 years. So t is 18. I'm looking for p of 18, which is 1.25 times 1.012 to the 18th power. So take 1.012 to the 18th power. Yep, that's 1.1012. 1.1012 to the 18th power, and round that to 4 decimal places. So I get 1.25 times 5.6701. Then we do that math, and we get 1.25 times 5.6701, and again rounding to thousandths, which is 3 decimal places. We have 7.088 billion. So that would be population growth, exponential growth. A can of soda is placed inside a cooler. As the soda cools, its temperature, T of x in degrees Celsius, is given by the following exponential function, where x is the number of minutes since the can has been placed in the cooler. Okay. So we have T of x equals negative 22 plus 46e to the negative 0.41x. Find the initial temperature of the soda and its temperature after 15 minutes. Round your answers to the nearest degree. Well, the initial temperature would be at time x equals 0. So we would have T of 0 equals negative 22 plus 46 e to the negative 0.41 times 0. Okay, so working with these exponents, bring everything else down. This simply is 0. E to the 0 is 1, so we have negative 22 plus 46, which is 24 degrees Celsius. Now we want to know what the temperature will be after 15 minutes. So T of 15 is equal to negative 22 plus 46 e to the negative 0.41 times 15. So bringing everything down, T of 15 equals negative 22 plus 46 E, and then our negative 0.41 times 15 to the negative 6.15. Okay, again, bring down to 15, negative 22, plus 46. So to get e to the, on my calculator, I hit second in the natural log. Now, to get negative, don't hit the subtract button. Make sure you hit the little negative button. Typically, it's down by the enter button or the equal button. It looks something like this, typically. So don't forget the negative, 6.15. That gives us that, and 0.002133482. And I'm just going to go ahead and multiply that by 46 and not get a whole lot. Negative 22 plus 0.098. Which gives me negative 21.902. The nearest degree would be negative 22 degrees Celsius. Let's check our math here and see what's going on. 0.41 times x is 15. 0.41 times 15, 6.15. E to the negative 6.15 equals, get that. Okay, multiply that by 46. We get this. Let's go 1,4. And this is 186, which rounds the nearest temperature is negative 22 degrees. So in 15 minutes, the can went from 24 degrees Celsius to negative 22 degrees Celsius. That's pretty quick. Okay, so now we'll look at exponential growth and decay function. For the initial amount, y sub 0 greater than 0, the equation y equals y sub 0 e to the kt defines a growth function if k is greater than 0, growth meaning increasing, and defines a decay function if k is less than 0, or a decreasing function. So determine if each of the following functions is a growth exponential function or a decay exponential function. So what is k here? K equals negative 0.9. So this is decay. Okay, here k equals 1.5. So this is growth. So let's look at real world use of this. According to U.S. Census Bureau, the world population reached 6 billion people on July 18th, 1999, and was growing exponentially. By the end of 2000, the population had grown to 6.079 billion. The projected world population in billions of people T years after 2000 is given by the function defined ft equals 6.079 e to the 0.0126 times t. So now we want to know, based on this model, what will the world population be in 2015? Well, that's 15 years. So T equals 15. So F of 15 equals 6.079 E to the 0.0126 times 15. So 0.0126 times 15. So I get 6.079 E to the 0.189. So E to the 0.189 times 6.079 gives me 7.343. I get 37 because I didn't round previously. Billion. In what year will the world population reach 8 billion? So that means that 8 equals 6.079 E to the 1.1 or 1.0126 T. Okay. So we can divide both sides by 6.079. 8 divided by 6.079. That works out well. 1.316 followed by a couple zeros, so we'll stop there. And this is E to 0.0126 T. Now, if I take the natural log of both sides of this, and I can do that, I get the natural log of 1.316 equals the natural log of E 0.0126 T. So we'll bring this down still, natural log of 1.316. And using my principles, I have 0.0126 T times the natural log of E. And we know the natural log of E is 1. Because if you remember, natural log of E is log base E of E, which is 1. So now I can divide both sides by this to get T. So the natural log of 1.316 divided by 0.0126 equals T. Now, when calculating this, don't forget to close your parentheses before you divide. So we hit the ln button. It opens parentheses for us. 1.316 close the parentheses, divided by 0.0126, and we get T equals 21.79, which would mean during the year 2021. Let's go real quick. Little aside here. And let's see what it is. World population in 2021. So pretty dang close. Now, keep it in mind that this, I believe, is the world population at the beginning of 2021. And if you remember, I find that we're looking at 3/4 of the way through. So yeah, I think this is a pretty good setup. Okay, how would we set up this problem if we wanted to know when the population would double from the size in 2000? Well, what's the population in 2000? Was it 6.079 times 2, which is 12.158. So we just simply set it up as 6.079 e to 0.0126 t equals 12.158. Now there's something interesting. This is a term that is used. It's called doubling time. Just out of curiosity, let's take this a little further. Let's go ahead and divide by our 6.079, and we get e to the 0.0126 t equals 2. If we take the natural log of both sides, natural log of 2, that gives me 0.0126 t equals the natural log of 2. So t equals the natural log of 2 over 0.0126. Or for doubling time, t equals the natural log of 2 over k, which is our growth rate. This is an interesting thing to consider, but this is what we're looking for. Right here is the equation we would use to find the doubling time. Now what about an exponential function? So if 800 grams of radioactive substance are present initially, and 2.5 years later only 400 grams remain, how much will of the substance will be present after 4 years? So we're talking exponential, we're talking y equals y sub 0 e to the kt. And we know our initial amount is 800 e to the kt. So then we're told when y equals 400, t equals 2.5. So looking at this equation, we essentially have 3 variables. Here we're given 2 of them. So substitute in y equals 400, 800 e to the k times 2.5. So we can divide by our 800 and we get 0.5 equals e to the 2.5k. Take the natural log of 0.5 and we have 2.5k divided by 2.5, and k equals the natural log of 0.5 over 2.5. And if we solve this, we get k equals negative 0.2773. So that's the first part of our problem. Now we want to know how much will be left after 4 years. So now we know t equals 4, and we know k equals negative 0.2773. So going to our original formula here, we're looking for y. 800 times e to the negative 0.2773 times 4. So we have 0.2773 times 4 I get equals 800 times e to the negative 1.1092 e to the negative 1.1092, and I get 800 times 0.3298, and that gives me 263.84 grams. That's how that works. This is how they calculate carbon dating. It's, so that is all for this section. Have a good night, and I shall see you next time.